So the last video cut me off a little bit. I just missed the end of it, so all we did was rewrite this in a different order. You didn't have to. You can leave it like that. On to number 12 we go. It says use logarithmic differentiation, and here's what we're given. Usually that means they've given you a fancier function. You know, multiple parts. Maybe it's a big product or a big quotient. This one's not too bad, but we definitely would have to do some quotient rule as well as some power rule and chain rule in this if we didn't rewrite this. So what we're going to do is take the log of both sides. So that looks like this. ln y equals ln of all of that stuff. And I'm going to go ahead and rewrite this as x minus 3 to the 1/2. And then we'll go x plus 5 to the 4th. And then rewriting this on the right side, oops, we'll end up with a 1/2 ln of x minus 3. And then we'll go minus, because it was a division, for ln of x plus 5. And at this point, we're ready to take derivatives. So if we go like this and throw a dx out in front, what we're saying is take the derivative of each of those three messes. All right, so the first one will just be 1 over y dy dx. Second one's got a 1/2 out in front, but 1 over the stuff times the derivative of the stuff. Next, 4 times 1 over the stuff, again times the derivative of the stuff. Can't get much easier than that with our ln's. Okay, so we're going to do two things in this next step. One of them is we're going to clean up this and clean up this, but while we're at it, we're also going to multiply both sides by y. That'll get the left side to be a simple dy dx, because that is the ultimate goal. So on the right side, we'll have a y out in front, and then we'll have a 1 over 2 times an x minus 3 minus 4 over an x plus 5. Again, the 1 times 1 doesn't do anything. The 2's on the bottom, the 4's on the top. This is almost your final answer, but you would probably want to rewrite it so you have all x's on the right. So change your y out to what it was, which is x minus 3 in a radical over x plus 5 to the 4th. And then inside, you can just leave that stuff as it was. Oops, that's supposed to be a minus, not a plus. So that would be a minus 4 over x plus 5. And I believe that's my final answer. Let me double check here. Looks good. Yeah, if you'd like, you can distribute the 2 into the x minus 3, but you don't need to. In fact, I prefer if you don't. But either way, if you had done it, not a big deal. Next up, 13. Excuse me. We were given y equals e to the negative 2x with the cosine of 5x afterwards. Now, I'm hoping you see it already, but this is a product, which means we're thinking product rule. So there's an f, there's a g. So to go find the derivative of this, we need to do the product rule. So here goes. dy dx. We're going to go with f first, times the derivative of g, which is e to the stuff, times the derivative of the stuff. And then we'll go plus g, excuse me, that was g and f prime. Now we'll go f times g prime. And the derivative of g is the derivative of cosine, which is negative sine of its stuff. Don't change the stuff. Times the derivative of its stuff. All right, now it's just cleanup time. Any coefficients and algebra stuff you usually put out front. So negative 2 e to the negative 2x, cosine of 5x. And then next over here, we got the negative and the 5. We can put those out front. Minus 5 e to the negative 2x. And then we got a sine of 5x. This is a pretty solid answer right there, but I do see something that we can factor out. And that would be the e to the negative 2x. And that's fairly common. So we'll do that. And then because this one leaves a negative 2 behind and a negative 5 behind, reordering them doesn't really make a difference. It'll still be a negative and a negative. Sometimes if that's a plus out here, they'll put the 5 out in front. So that didn't happen here, so we'll leave it as is. So inside we got this, and then we got a minus 5 sine of 5x. And again, either one of those is a great final answer. So that's it for 13. Moving on. 14 coming up. Find the derivative of y equals e to the 3x to the 5th. So that's as simple as e to the stuff, it's a repeater, times derivative of the stuff. Technically, you're done. A lot of times we'll put the basic algebraic stuff in front of the e, but it doesn't really matter either way. So that's that one. Next, 15 coming up. All right, so 15, they got the radius of a circular oil slick expanding at a rate. So that's a dr dt. It said expanding, so that's positive at a rate of 2 feet per second. Sorry, I don't have the words on the page here to show you what I'm doing, but you've got it in front of you. How fast? How fast? That's a rate, so that's a d something dt. How fast is the area? That's a dA dt. It said it's increasing, so we're expecting a positive result for that dA dt. And they said when the radius is 25 feet. So we would jail that guy, and we'll use him later. So keep your eye on the prize. We have to have an A involved. We also have to have an R involved. So it's a circle. Pretty straightforward. A equals pi r squared. So then we'd have dA dt equals pi times 2r dr dt. Other people like to go straight to the 2 pi r dr dt, which is a nice little connection between our area and our circumference. So the derivative of area of the circle is the circumference. It's pretty sweet. And at this point, we're ready to plug in. So dA dt equals 2 times pi times the radius, which is 25, times our dr dt. So that would be a 50 times 2, that would be 100. Put a pi on it, and its area, so that would be feet squared per second. And that would be it for number 15. Number 16 coming up. 16, we've got some trig. It's a cosecant function of e to the 6x. So we know our derivative of cosecant, hopefully we do. It's a repeater, and it's a negative repeater because it starts with a c. So that'll be a negative cosecant of stuff, cotangent of stuff, times the derivative of the stuff, which would be e to the 6x times 6. And we'll take the 6 and the e to the 6x, put it out front with a negative sign. That's just a reordering, not a big deal. And then we got the same old trig stuff. That's not going to change, we're just rewriting that part. All right, not much to it. Know your derivative rules, know your chain rule, and you are done with number 16. 17, how about some red? 17, it asked for the derivative, dy dx, if we're given cotangent y equals e to the 4x plus ln of 3x, which I'm going to rewrite as ln of 3 plus ln of x because I can. It's a nice little trick because now when you take the derivative, this one will go away. Derivative of cotangent starts with a c, so that'll be a negative cosecant squared of y, but then times the dy dx, of course. Derivative of e to the 4x, I think we're at that point where we can start putting the 4 out front right away and not do it as two steps. Derivative of constant is gone, and out here you get a plus 1 over x. Time to move the cosecant squared over to the right, so that would turn into a simple dy dx on the left, and then we could just have our 4e to the 4x plus 1 over x on top of a negative cosecant squared of y. And that's a good final answer. We could leave it there, although we don't really like a fraction within a fraction. So we could change this negative cosecant squared of y. Remember, that's negative 1 over sine squared of y. So we could move that up and write our final answer like so. We'll put a negative out in front of the whole thing, and we'll put a sine squared y over here. I do believe that would be the correct multiple choice answer if this were a multiple choice test. All right, cruising right along. Let's go to number, not 18 because we're skipping those for now, and 19. 20 is next. It says given that the radius of a sphere increases So dr dt is positive 0.002 meters per second. When, we have a when that we're going to jail up when the r is 1 meter. Don't use that till later. Find the rate. I'm hearing goal. Find the rate, so d dt of something, at which the volume increases. And they gave us the volume formula, which is nice. So it's 4 pi over 3, or 4/3 pi, r cubed. So taking a derivative, we got dv dt. Oh, I should pause for a second. Our equation has a v and an r in it, which is great because we're looking for dv dt and dr dt to be involved. So, all right, so 4 pi over 3 times the 3r squared dr dt. The 3's will cancel, so we get a nicer formula. It's just dv dt equals 4 pi r squared dr dt, which coincidentally 4 pi r squared is the surface area of a sphere. So kind of nice little connection there. All right, we are ready to plug in. So we're going to go take our r, stick it in there, and then dr dt is 0.002. If you multiply that all together, let's see here, I think I've done this one already, we get 0.008 pi, and that would be in meters cubed now per second because we're dealing with a volume. And it's positive, and that makes sense to us because they said that the radius was growing, which means the volume should be growing as well. If you went ahead and put that into decimal form with the pi in your calculator, it's something around 0.025 meters cubed per second. But you don't have to do that. All right, I think we got time for at least one more. So 21, kind of an interesting question. A point P moves along a curve whose equation is y equals square root, but I'm going to rewrite that as x squared plus 144 to the 1/2. They said P is equal to 5/13, and they said when in front of that, so that'll be jailed. That's our x and our y. So y is increasing at a rate, so dy dt is already given to us at 5 units per second. And then the goal is dx dt. How fast is x changing? So we'll take a derivative of our equation. Dy dt equals 1/2. Stuff to the negative 1/2. Moving quickly here, see if I can beat the clock. Almost up to my 15-minute limit. The 2's will cancel, so our derivative will be an x over the square root of x squared plus 144. Oops, I almost forgot the most important thing. There's a dx dt over here, and that's what we're looking for. So dx dt is over here. Let's see, the 2's cancel. X is on top. You got a dy dt over there. We could rewrite this whole mess with dx dt by itself. Or we could just plug in at this point. That's really a decision that you could make at this point. So I can plug in the x. I think we'll just do that. We'll just make it numbers first. So dy dt was 5. X was also 5. So down here we'll have a 5 squared, which is 25 plus 144. And then we have a dx dt. So moving over here, we're going to have, let's see, that's square root of 169, which is 13. So we have 5 equals 5/13, and with the dx dt on it. If you were to just go multiply both sides by 13/5, we get a nice answer. Dx dt equals 13, and that would be units per second. All right, so there you have it for number 21. And I think we're just going to have to stop it right there. And yeah, thanks for watching.